A graph can be represented using the adjacency matrix. For a directed graph, if there are vertices from 1 to n, then we will make n into n matrix in which the entry in row I and column j is 1 or true if there is direct edge between vertex j to vertex I, and we will set it with 0 if there is no direct edge. To represent this graph into an adjacency matrix, we need a matrix of 5 rows and 5 columns because there are total 5 vertices. In this matrix, row 1 represent vertex 1, row 2 represent vertex 2, row 3 represent vertex 3, row 4 represent vertex 4, and row 5 represent vertex 5. Now we will start from vertex 1. Row 1 represent vertex 1, so we will fill row 1 according to vertex 1. Is there any edge from vertex 1 to 1? As you can see, there is no self loop. There is no edge from vertex 1 to 1. So we will write 0. From 1 to 1, 0. Is there any edge from vertex 1 to 2? Yes. So we will write 1. Is there any edge from vertex 1 to 3? Yes. 1 to 3, 1. Is there any edge from 1 to 4? No. 0. Is there any edge from 1 to 5? Yes, there is a direct edge from vertex 1 to 5. So we will fill from 1 to 5 with 1. Now we will start filling row 2. Row 2 represent vertex 2. From vertex 2 to 1, there is no direct edge. So we will write 0. From vertex 2 to 2, there is no self loop. We will write 0. From vertex 2 to 3, there is a direct edge. We will write 1. From vertex 2 to 4, a direct edge. No, there is no direct edge. 0. Vertex 2 to 5, no direct edge. 0. Now vertex 3. From 3 to 1, no direct edge. 0. From 3 to 2, there is a direct edge. Yes, 1. From 3 to 3, no direct edge. 0. From 3 to 4, direct edge. 1. From 3 to 5, no direct edge, 0. As you can see, there is no outgoing edge from vertex 4 and vertex 5. So row 4 and row 5 will be filled with zeros. Matrix representation of a graph is also useful if you want to find out the in degree and out degree of each vertex. For example, if you want to find out the in degree of vertex 1, then all you have to do is to take the sum of row 1. The sum of row 1 in the adjacency matrix is the out degree of vertex 1. So if you calculate the total number of 1 in row 1, that is 3. 1, 2, 3. So out degree of vertex 1 is 3. Similarly, if you want to find out the in degree of vertex 3, the in degree of vertex 3 is 2. All you have to do is take the sum of column 3. This time column. If you want to find out the out degree, then take the sum of row. If you want to find out the in degree, then take the sum of column. So in degree of column 3 or vertex 3 is 2. The matrix representation of a graph is also useful for path counting. For example, a path of length 2 from vertex I to vertex j in a graph exists if there is some vertex k such that there is an arc from vertex I to vertex k and an arc from vertex k to vertex j. Hence, both the I k entry and the kj entry of the adjacency matrix of G must be 1. For a weighted graph, there is some cost or weight associated with each arc. For example, while modeling communication network, each arc has some weight. So this time, instead of writing 1, if there is a direct edge, instead of writing 1, we will write the cost of the arc. For example, the cost of the arc from vertex 2 to vertex 1 is 9. So instead of writing 1, we will write 9. But what we're going to do if there is no direct edge? In that case, we will write 0, -1 or infinity. For example, there is no direct edge from vertex 1 to vertex 3. So instead of writing 0, I'm writing infinity here because there is no cost available. So I will write infinity. If you notice in this matrix, in diagonal position from vertex 1 to 1, 2 to 2, 3 to 3, 4 to 4, and 5 to 5, these diagonal positions are filled with 0. It means that to move from vertex 1 to 1, there's no cost. So I will recommend to use infinity sign if there is no edge instead of using 0. A complete graph is a graph in which there is an edge between each pair of vertices. If your graph is a complete graph, then you can find out total number of edges by using this formula n into n minus 1, where n is total number of vertices. Total number of vertices in this graph are 4 and the value of n is 4. So you can find out total number of edges by using this formula. 4 into 4 minus 1, that is 12. So total number of edges are 12. You can also represent graph by using linked list. If graph is to be represented in linked list, it must have two types of node, vertex node and edge node. Vertex node has information of vertex linked to next vertex and linked to edge list, while edge node has linked to vertex node and linked to next edge node. First, we're going to list down all the vertices and list them with each other. There are four vertices A, B, C, D. So, vertex A is connected with vertex B is connected with vertex C, and vertex C is connected with vertex D. Then we will connect and or add link to all the edges with each vertices. For example, vertex A has two edges from A to B and A to C. So the edges information of vertex A is connected with vertex A node. So A is connected to vertex B, edge B and edge C. While B has only one edge from B to D. So vertex node B is connected with D edge. Similarly, C is connected with edge B and D is connected with edge B. That's how you can represent a graph using a linked list.